Okay, so let's continue with this discussion. Please, now we are going to explore yesterday.
People sometimes in photography go away, right? What is present as the photo is, at the 18th century was Fresnel and Poisson. It was a debate. So the question is light is the light a wave or particle? So Fresnel devised one of the most striking experiments, that you can, if you like, you can like as you believe, is that if you shine light in a very perfect sphere, here, and you put a screen here, you're going to see just in the center of the shadow, there is a bright spot. How's that possible? The only way to explain this is consider that the light behaves as a wave. And after this experiment, Poisson was making fun of this. I don't know if Poisson didn't get Poisson neither Bresnel did the experiment, somebody else did the experiment, and there was this, that was it, complete. Somebody did the experiment and showed it that yes. So before the 20th century, the end of the 19th century, nobody questioned if light was a wave or not. It was a wave. But after this, after Einstein came around to explain the photoelectric effect, the only way to explain the electrophotoelectric effect is considering that light also behaves as a particle. So the only question was, what is light? Is a wave or a particle? It depends, right? It depends. So are both or neither, right? Anyways, so this is the expression they found, they developed to understand the electron, like h bar omega. This, sorry, I forgot this. What is chaos? Look this. I stress on my students. Looks so beautiful questions, symmetrical. See, once you see this, you will remember for life. It's so easy to remember and it says a lot. But what is K? Uncle, what is K?
Wave number.
What is the wave number, please? You forgot that. With my house, I will call myself. You see? So it means that the momentum is h over lambda. This is the famous, so momentum is h over lambda. That is the famous of the Broglie equation. Right? Why? Because the Broglie proposes for any kind of free particle, right? So we have this and this. So any kind of particle has an associated wavelength. But what is waving? So here comes interpretation. What is waving? But if you accept in the other hand, we accept the Copenhagen interpretation, Max Born, Niels Bohr, these guys. So why is the collapse of the wave function? So you have to accept things that we just consider, without question, right? In one hand, there are many interpretations, but the two main streams at that time was this, the Copenhagen interpretation, and you have to accept the collapse of the wave function, or this particle, any particle that is moving has an associated wavelength. So that's it, what is wave? See? So you have to say two things that we cannot even measure, right? Wave income we cannot measure. And what is waving here? We cannot measure. So as you can see, this is, so many people here, important people. Dirac took Schrödinger equation and make the relativistic version. And thanks to that, he discovered the antiparticles. This, it is very nice. There is a couple of weeks ago there is a very short documentary about the Dirac equation. I strongly recommend to watch. You're going to enjoy. I will share this later, for your improvement of your knowledge on quantum mechanics. Okay. You have Heisenberg. Perhaps Heisenberg was the first person to propose the first formal theory in quantum mechanics, right? Heisenberg, when he was ill, by the way, it's very interesting the history of Heisenberg, right? He was ill, he went to an island and said, okay, I'm relaxed, I try to recover. And those in that island, that I don't know if it exists right now because they bombed in the Second World War was bombed. He developed a the matrix version of quantum. Okay, the matrix, and it was amazing, amazing work. Like, after a couple of months later, he also proposed in a very famous paper the Heisenberg uncertainty, fundamental. Well, you have Niels Bohr. Niels Bohr was this this intuitive physicist, but using classical ideas in crystal magnetism, he was able to cast and to propose the first model for explaining the hydrogen atom, the Bohr atom. It's successful, because it used the key idea of Niels Bohr was that he realized that Einstein and Max Born realized that energy is quantized. Niels Bohr, perhaps we are thinking that perhaps he was thinking maybe the action also is quantized. But the action, the units of action and the units of angular momentum are the same, so the angular momentum should be quantized. And it's very amazing to know, and that's the reason why he got this famous model and no problems. But then, anyways, we're going to come to this guy, Erwin Schrödinger. So Erwin Schrödinger proposed the Schrödinger equation that is fundamental for all branches that is dealing with understanding the atom and the atomics. And as you can see here, is the experiments that lead to quantum mechanics. So I suppose most of you were exposed to this. So you know the photoelectric effect. We studied the photoelectric effect here. Cavity radiation, right? The black body spectrum. This cavity radiation was a problem from the 16th century was already 17th century was already a problem was known. Okay. Other problem was the discrete atomic spectral lines. Remember this? The only way to explain this is the quantization of the energy levels of the atom. The Frank-Hertz experiment, of course. And you have the Stern-Gerlach. Remember the Stern-Gerlach experiment to explain this with electron speed, right? I don't know if you study the Frank-Hertz experiment. Remember this? You excite the atom and you start to see this kind of. I remember a device when I was your age. We did the experiment, and I think really UC maybe they have this device. It's with mercury gas. You excite mercury gas and you start to see this kind of pattern. This is the energy quantization model. You have this. You have Compton scattering. Remember the Compton also they also prove the particle nature of light, right? So because Compton said the interaction of one electron with one photon with electron. So the only way to do this is considering that the photon is also a particle. So this Compton scattering and photoelectric effect, the only way to explain this considering that photon is a particle. And of course the Rutherford, the very famous experiment. Remember the Rutherford when he was working in the Cavendish, I think it was in Cavendish lab. He asked his postdocs to do this crazy experiment. They were playing with alpha particles on thin films of gold. So all the scientists were put in the back of the detectors to see the cross sections, right? But Rutherford somehow he realized that I don't know how. He said, let's see what happened if there is a chance to see this the alpha particles bouncing back. But how is that possible? This is for everyone, for postdocs, it's nonsense because it's like to shot cannonballs on a paper and this cannonball will bounce back. And yes, the experiment came to Rutherford and said, wow, we found the thing. So from Rutherford appeared the idea that everything in the atom, all the mass is concentrated in some point, in the nucleus, and the electrons are around. But that model has a problem, because everybody said, okay, Rutherford, and that's the reason Rutherford didn't get, okay, he got, of course, he was Nobel Prize in chemistry, but the problem is that how you are going to sustain that model, because if the electrons model is at that time, if the electrons are accelerated, they has to radiate and the electron has to collapse to the nucleus. So it's impossible. So they still didn't understand the quantization of the energy of the electrons around the atom. But that was, that was the first step. And after, came Niels Bohr, and they explained this kind of the things. You might ask, what about Max Born? Max Born was the head, he was the head of all these guys, young guys doing quantum mechanics. Niels Bohr, even Oppenheimer, Niels Bohr, Heisenberg, all this. He was hosting them, in Denmark, and he fully understood the theory, and besides, when Schrödinger proposed his theory, the Schrödinger equation, when he proposed this stuff, when he proposed the Schrödinger equation, the wave function, Schrödinger believed that this wave function, this famous equation, right? So when he proposed this famous equation, when he proposed this famous equation, this is the stationary Schrödinger equation. He thought that this wave function was real. So he says everything has to be waving. But when he saw this, the only way to solve this, is to accept that the wave function is complex. So it's impossible to measure, it has no physical meaning. So Max Born came to say, look, everything is fantastic because it's just what we needed, but this wave function that you are disappointed, in fact, the physical one is the probability, the density probability that is right. So the density of side conjugate times, right? So this has a physical meaning, it's a probability. And that is the reason why Einstein didn't like at all this, because he says has to be deterministic, nature has to be deterministic, and that is the reason that the big debate between Niels Bohr and Einstein, saying that all this. Okay, I'm going to stop here 5 minutes, please, before you go to no coffee, nobody go coffee. Okay, I'm going to stop 5 minutes before we continue. It's a very important concept we are reviewing here, and that's it. So this is the last time, just in case. The last time you review quantum mechanics in this university. After that, you are going to review somewhere else. So anyways,